Here, a few meters away, there is the Galileo chair. Did you see it? What did you feel?
I did. I found it very inspiring. I was particularly impressed that his students, I'm told, built it for him. So they must have loved him very much. They must have really appreciated the knowledge that he shared with them. But of course, knowing that it was Galileo's, Galileo's probably the most important scientist of all time. So it just is very inspiring.
One of Galileo's first and most important observation was about supernova, that are very important also to your work. Why are supernovas so important in astronomy and astrophysics?
Right. They've had different uses over time. In Galileo's time, there was the question of where were they? Were they in our atmosphere? Were they further out? And people like Galileo would see if they could measure parallax of them to determine where they were. In my work, we also use supernovae to figure out where they are, but now in this case, we know they're very far away, and we use their brightness to tell us how far away they are. But more importantly, we use them as tracers of the expansion of the universe. We use them to tell us how fast the universe is expanding today, and we look at distant ones whose light has been traveling to us for billions of years to tell us how fast the universe was expanding in the past. And so this is one of the best ways we have of seeing how the expansion rate of the universe has changed over time.
You have shown in those studies that not only your universe is expanding, but it is accelerating. Can you explain to us why this happened?
Well, the simple answer is nobody knows for sure. It's attributed to something called dark energy, which is a kind of energy present in the universe. And if there is such an energy, then Einstein's theory of gravity, general relativity, says that it should accelerate because there would be a kind of repulsive gravity associated with that energy. But why that energy exists, how much of that energy there is, has that energy been around all the time? These are questions that we have. Or even, is there that energy, or is there some other explanation? Right now our best guess is that there is dark energy, but that's a very active area of research.
Scientists say that dark energy is about 70% of the whole universe. How can we measure dark energy and also dark matter?
Right. Dark energy and dark matter are so important together. They make up about 96% of the universe, but they're incredibly weak. And so we can't really see their effects unless we look across the entire universe. So seeing them here on Earth is very difficult. They don't emit any light, and their gravity is exceptionally weak because they don't clump. Dark matter doesn't clump together to make a basketball or a rock. It's always in this form of a stream of particles that are loosely present in the universe at low densities. Same thing with dark energy. It's very low level of energy. And so we only notice its presence when we add it up across the universe. And so that's why astronomers have to use telescopes to learn about dark matter and dark energy. And that's why it took so long to discover they were out there.
This is probably a stupid question, but you think in this room by now there is dark energy and dark matter?
Oh yeah, there is dark matter and dark energy in this room, certainly, but the amount is so slight we couldn't even power a small light with it. And in terms of dark matter, it would be very difficult to even find the dark matter particles in the room because it doesn't interact very much. This has been a great struggle of physicists, is to actually isolate dark matter in the laboratory. And people are working on that. It's just very difficult.
And yet, what's next? Will the universe continue to expand more and more and get colder and colder? There are other theories about.
Right. So the future of the universe depends specifically on knowing and understanding exactly how dark energy operates, whether it's constant in time, whether it can change in time, whether it can increase or decrease. So if it's what I would say is the most likely possibility, that it's constant in time, then the universe will expand forever, it will get colder, objects will become so far separated that there's not even the ability for light to reach us from distant objects, and that would be the future. However, it's also possible still that the dark energy could change over time and could still collapse the universe. So that's one of the reasons we want to understand more about dark energy.
You won the Nobel Prize when you were only
42, I think so.
41, yeah.
41. What's the impact on the career of the scientist to win this big prize so early?
I think the Nobel Prize, for me, has, if anything, been inspiring. The recognition that you work on things and those things can turn out to be really fundamental and interesting, that I guess, in my view, anybody could win a Nobel Prize if you're, you work hard and you're lucky. You don't have to be, Albert Einstein to do it. But mostly the inspiration that I've drawn from it of just how deep and profound some of these questions are, that they can sort of be like, the old story about a sweater and having a loose thread on the sweater. And, maybe it's just a loose thread, but, you pull on it and it might unravel the whole sweater. And in science, we're often searching for those threads that can sort of unravel our picture and teach us something new about the universe. And so I found it in that way very inspiring.